Okay, this video is chapter 35E. It's from this book here, The Medical Reformation by me, Pete Rogers. Okay, we're starting with image 3523, which is on page 492. And this is the Yerkes-Dodson curve of stress versus performance. And what it's all about is that there's an optimal level of stress. You have to have enough stress to be energized, enthusiastic, motivated, and ready to go. So if you don't have any stress, if you don't have any sympathetic autonomic nervous system activation SANS, then you're kind of lazy, inattentive, unmotivated, half-assed, bored. Okay, you got to be pushing yourself a little bit. So that's in the flow, if you will. Meaning that this is called eustress, EU stress, true good stress. This guy named Krashen wrote about, learning language. You want what is called comprehensible input. It's a little bit challenging for you, but you can do it. Okay, so anyways, that's sort of good stress. Excessive stress impairs performance. That's distress, anxiety, being real upset about something. So that'll decrease performance. So that's basically what it comes down. Anytime you move, you increase stress a little bit. So it's like if you wake up at night to go to the bathroom, you don't want to move around too much, or you like wake yourself up by increasing your sympathetic activation, your stress hormones, so to speak. Okay, but at the same time, you got to get yourself into the right amount of enthusiasm in order to perform well academically or in sports. Okay, here's the next curve showing you sort of a seesaw between growth, which, we're talking, this is a book, the chapter's about cancer, so you don't want anything that's going to activate growth. You don't want mTOR. mTOR is mammalian target of rapamycin. That comes from the island of Rapa Nui, where they have the Easter Island statues. They found this fungal thing called rapamycin, and they use that to block mTOR. mTOR is mammalian target of rapamycin or mechanistic target of rapamycin, and basically it's a nutrient sensing pathway that when nutrients are adequate, it tells the cell to grow. So if you've got cancer, you don't want to be activating that pathway. If you're 20 years old, lifting weights, trying to gain weight and get bigger, stronger, faster, okay, fine. But, you're over 35, you're not in competitive athletics anymore. You don't want to be accelerating mTOR because you have something else called the Hayflick limit. You only get about 60 cell divisions in your somatic body cells. So there's stem cells that are in special locations like in the gut, and there's also germ cells, which are reproductive cells in the ovary and the gonads, male testes. But the other cells, they're just regular somatic cells. Soma means body. So those cells only get about 60 divisions, and then they die. So you don't want to be accelerating the rate at which they replicate. So what activates mTOR? It tends to be the rate limiting step, tends to be like leucine. That's an amino acid, much more common in meat. It's a branched chain amino acid. So the young bodybuilder might take a protein supplement with branched chain amino acids. But by the way, I think amino acid protein supplements are stupid. They're often kidney toxic, nephrotoxic. But in terms of in an older adult, leucine is often a rate limiting step. Things that elevate insulin levels will activate mTOR. Elevated levels of iron have a tendency to contribute to activation of mTOR. Like a contractor getting ready to build a building, it has to have all the building materials available before it builds. So what I'm saying is you want to avoid things that cause insulin resistance. They'll tend to lead to elevations in insulin-like growth factor, like fat especially, saturated fat especially, which is animal fat. Animal proteins also going to lead to insulin resistance and hyperlipidemia. It sort of induces a mild anabolic state in the human body and elevates blood lipids. Let's see what else. Estrogenic chemicals also, you don't want those. Those will cause proliferation of cells in the breast, in the uterus, and in the prostate. So they're all going to increase cancer in those areas in general. You want to get your sleep. If you don't sleep well, you'll be stressed out and get the same hormones elevated. Cortisol and catecholamines, which is epinephrine and norepinephrine, are the hormones of psychological stress. So that's bad because that's going to lead to elevated blood lipids, elevated blood cholesterol, blood glucose. The psychological effects of the stress with the elevated cortisol, they're going to suppress your immune system. Cortisol shuts off your immune system. Your immune system is what removes cancer cells. So you don't want chronic high levels of psychological stress unnecessarily. And like I said, caffeine elevates the same hormones, so does sleep deprivation. So those things are bad. Okay, excessive sodium is bad. It'll cause a tendency. It does a couple negative things you don't want. It'll contribute to insulin resistance. It'll tend to get you to eat more. It'll tend to raise your blood pressure. It'll tend to lead to increased excretion of potassium and magnesium vasodilators. It's all bad. These are the things you want more of. You want to spend more time in PANS, parasympathetic autonomic nervous system. That's the brake rather than the accelerator, sympathetic autonomic nervous system, SANS. After you exercise, you activate a pathway called the AMPK pathway. You can also abbreviate AMP and then K. So it's the adenosine monophosphate, as instead of ATP, adenosine triphosphate, which is basically energy in a cell, like a $20 bill is an ATP, activated protein kinase. And so what that happens is when you've been exercising a lot, you're a little tired. So your ATP storage levels in your cell become kind of low, depleted. So what happens is your body activates this AMPK pathway. It's like the opposite of mTOR, and it sort of says, look, we cannot grow right now. We are too low on energy. We need to reestablish our energy levels. And so let's just take some time to make some ATP, and you might undergo, mitophagy, where you sort of check out your mitochondria, make sure they're all functioning well, recycle the old ones that aren't working well. So this is like a maintenance phase, and that's what you want. A lot of the people I've seen make the greatest recoveries from metastatic cancer and be alive 20, 30, 40 years later. They were exercising a lot, like look at Ruth Heydrich. Look at that Janet Murray lady in Australia who ran a marathon every day for one whole year. She's alive more than 20 years after metastatic cancer, and there's other ones too. So what else? Keeping a thin body weight. If you're fat, you tend to get a spillover effect, and you're releasing fatty acids into the blood, causing hyperlipidemia, increasing activation of mTOR, bad stuff you don't want, increasing inflammation, nonspecific, etc., and inactivating your NK cells, which are part of your immune system, remove cancer cells, all bad. Sleep, love, it's sort of like a happy, time around friendship, positive people that have a similar purpose to you, whatever that goal might be. All of that relaxes you, puts you into more parasympathetic. Religious people, lowers your stress. You sort of give it over to God, some of it, and you see a purpose in your life, meaning, okay? All that stuff makes you stronger. Attitude of gratitude. By lowering your stress, you increase the function of your immune system, so it's good for you, okay? Okay, so that's an important point. You want to slow down mTOR, and part of what it's about slowing mTOR is so you arrive later at the Hayflick limit. This guy Hayflick, I think his name was Leonard Hayflick, is a molecular biologist working with human tissue cultures, and he found that human somatic cells only divide about 60 times. So you want to avoid anything that speeds that up, or you die sooner. So you basically accelerate towards aging when you're constantly unnecessarily overactivating mTOR. Okay, and the reason for this is cells tend to lack, most of your non-stem cells lack telomerase enzyme in large amounts. So that you'll have a tendency to keep shortening your chromosomes every time a cell divides. Eventually, the cell will divide into the chromosomes themselves. There is some evidence. This lady Blackburn, she won the Nobel Prize for discovering the enzyme telomerase. I don't know the exact year, around 1990 or something. Dean Ornish did a study with her too, where they found that stress reduction led to actually elongation of telomeres, not just slowing down of their loss, but some elongation of the telomeres, which are like the ends of a shoelace on the tip of chromosomes. So again, because DNA polymerase, the enzyme to copy DNA, can't get all the way out to the end of the chromosome, you have these things at the end of it that sort of protect the ends of the chromosomes. Because the chromosomes are going to shorten each time because the DNA polymerase can't get to the end of it. So what I'm basically saying is you don't want to accelerate cell division unnecessarily, or you end up arriving at the Hayflick limit sooner. The Hayflick limit means you've replicated so many times that now the telomeres are so shortened, they're shortened into essential genes that you need, and that are going to affect your mitochondria, and that's going to cause mitochondrial dysfunction. And when you got mitochondrial dysfunction, the cells inevitably are headed towards impending death. Okay, protecting mitochondria is like one of the most important things you could learn and could know. Okay, so we talked about when you exercise, you shut off mTOR, you activate AMPK, good. You can replenish ATP. High AMP, adenosine monophosphate, instead of adenosine triphosphate. ATP means the cell's energy is low. AMPK, in a sense, is the pathway that's activated when the cell is tired. Okay, mTOR is the pathway that's activated when you're just eating a giant meal and you're well rested. Okay, this shows about cognitive function, the life cycle of the sea squirt. When it's a juvenile, it has a brain, it swims around. Anytime a creature moves, it has to make a value judgment, what to go towards. It has to navigate, has to avoid obstacles. So it needs a brain. Like Voltaire had said, why do animals have brains but plants do not? Because animals move. The point of the sea squirt's life cycle is that when it's an adult, it attaches to a rock, becomes a filter feeder, and its brain is reabsorbed, completely recycled. You don't need a brain if you just sit on the couch watching TV all day. Okay. So exercise has got lots of benefits for the brain. It increases BDNF. One of the reasons to go through this is lots of cancer patients take chemotherapy and they get chemo brain, and it sort of dulls their cognitive function. So one of the best things you do to get it back is get your sleep, optimize your diet, manage your stress, and exercise as much as you're comfortable doing. Exercise increases BDNF, which is brain-derived neurotrophic growth factor, and that helps new neurons to form, neurogenesis. It contributes to synapse remodeling, synaptogenesis. You'll get increased brain glycogen storage, which is a good thing, like in the astrocytes, to store energy to help your brain cells. That's sometimes called glycogen supercompensation. You'll increase brain cell mitochondria. Making new mitochondria is called mitochondrial biogenesis. Again, a good thing for the brain. You will improve insulin sensitivity. When you exercise, you get the glucose type 4 transporters to move from the cytoplasm up to the plasma membrane of the cell. And that allows it to take in more glucose and have less need for insulin. So essentially, exercise does the same thing that insulin does in terms of getting more glucose into the cell. It's a very good thing for us. If I had diabetes, I would always walk right after eating. Okay, here's a couple of great books that can help any cancer patient you might know. This is the lady, Ruth Heidrich. I did an interview with her recently. I posted that video on YouTube. And she's an extraordinary lady. She's about 88 years old right now. And she's a lady who was diagnosed with metastatic cancer when she was in her 40s. And they told her she's going to be dead in a couple months, make a will, all that kind of stuff. And she said, no, I want to run a marathon. And she just kept running marathons. She was, Dr. McDougall helped her out, and he convinced her in like 1 hour of conversation to become a vegan. She went 100% vegan on the spot, okay? And she did fantastic. Okay, here's another lady with metastatic breast cancer, and she's a doctor, and she's really smart, and she talks a lot about it. And she emphasizes what she calls it God's way of healing, okay? And basically, 100% vegan, maintain your hydration, lower your stress. She's super Christian. She's like reading the Bible every day and stuff. And that's another thing I saw in a lot of people who live long from cancer is they're very religious. And like my mom lived 11 years, and I was stupid at the time. It was many years ago. I didn't know all this nutritional stuff. I could have coached my mom and helped her more. I wish I had known. When I was young, I just took it for granted that you go to the specialist and the specialist knows the most in their field. Later on, I learned that it's actually pretty easy to outlearn most medical specialists because they don't know the most important things about even their own fields. But I didn't know at the time. So anyways, I wish I had. And she has this whole protocol approach which basically emphasizes lower your psychological stress by being religious and eat the vegan diet, stay hydrated, and get your sleep, that sort of thing. Let me show you some of the other great books on here. This is the lady from Australia who ran a marathon every day. Her husband was a marathoner. They ran it together. I mean, that's incredible. If I ran a marathon, it would take me probably a couple weeks to recover. I'm not a runner. I used to run. I ran cross country, many years ago in high school, but I'm not a runner anymore. Anyways, these two are rather incredible. Running a marathon every day, 365 days in a row, all around the periphery of Australia. And she's alive like more than 20 years after being diagnosed with metastatic breast cancer. They told her the same thing as, well, it looks like you're practically dead, make a will. We can try chemo. And she decided not to get chemo. She actually had some minor form of almost like a homeopathy chemo briefly. You can read her book. It's a really good book. Okay, here's another book called Tripping Over the Truth. And this is Travis Christopher. Her name is Janet Murray. Travis Christopherson wrote a book, Tripping Over the Truth. Now, he's a good teacher of biochemistry, and he did a great job of explaining the metabolic theory of cancer. He's got YouTube videos. All of these people here have YouTube videos. She might be the hardest one to get YouTube videos on. You can find videos of her on other channels. Travis Christopherson, he did a great job of explaining the biochemistry of the metabolic theory of cancer. You know, he's a little bit affiliated with that guy Seyfried, Thomas Seyfried, who did a lot of good research on the metabolic theory of cancer, but both of them really don't know much about nutrition. I would not look to them as a guide for nutrition. I think their nutrition knowledge is far behind their biochemistry knowledge. Okay, sunshine is your friend. With sunshine, you get more vitamin D in a good way. It's better to get the vitamin D from the sunshine, and that strengthens your immune system. Will help you to prevent your cancer. It also does some other things. It releases nitric oxide precursors. That's why it feels so good to stand in the sun. So you get a systemic vasodilation as those are converted to nitric oxide. It also helps the body generate more sulfates for the endothelial glycocalyx, and that helps maintain your cell borders the way you want to, like for your blood cells and for your endothelial cells lining your arteries. It's all good. Okay, we're going to briefly talk a little bit about iron here. So iron is essential for life. Bacteria can't grow without iron. So if you look at an egg, the eggshell's permeable to bacteria. The yolk in the center is where the embryo is, the living creature of the future chicken. Okay, and then you have the egg yolk, which is mostly protein in the periphery. So the key thing to know is that the egg white has no iron in it. And the bacteria, even though they can get through the shell, they can't get through the egg white because of the lack of iron. And it's like a person who, you know, a human being by themselves without any supplies can't walk across the desert because there's no water. So what's the point of all this? The human body sequesters iron in order to prevent bacteria from growing. And sequestering iron also helps prevent cancer from growing. So you don't want high levels of iron in your blood. And so you want to minimize your dietary iron, unless you're iron deficiency anemia, which not many people are, you know, a young menstruating female most commonly, okay? But how come the human can't go across the desert? Because there's no water. Okay, so typical American men, by the time they hit their 20s, are done growing, they start rapidly becoming iron overloaded because they tend to eat a lot of meat and they tend to eat all these processed foods that are fortified with iron, which is a bad thing. They add it to. They're like shave off iron fillings into your food. It's stupid. I didn't know any better when I was young. I used to eat Raisin Bran cereal on purpose because it had the highest iron level. You know, I used to watch Popeye cartoons and he would eat the spinach to get the iron, and we thought that would make you stronger. Okay, the women start getting iron overloaded typically after menopause, once they stop menstruating. If they have a hysterectomy at a younger age, let's say for fibroids or something, they'll start becoming iron overloaded immediately after that. Okay, so in general, you take a look, you know, when you eat an animal, the iron's right in the center of the hemoglobin in the blood, okay, for binding to oxygen. So that's bad. That's another reason why you don't want to eat animal foods. When you eat a plant, the chlorophyll has magnesium in the center. You want magnesium. Magnesium is one of the most common deficiencies of Americans. The vast majority of Americans, I don't know the exact percent, somewhere in the 90s are magnesium deficient. So all you got to do is eat plants. You get magnesium right in the center of chlorophyll. Okay. Magnesium is a vasodilator. It works in conjunction with ATP reactions, and it also is needed to properly manage your potassium. Okay, so here's the point. Why is iron so bad? The reason iron is so bad is when you have excessive amounts of iron, you'll have more free iron getting into the blood, for example, or also getting into your mitochondria. Free iron can undergo what is called ferrous redox cycling. Ferrous means like rust in Latin. Okay, that reddish color. So ferrous redox cycling means that it can cycle back and forth between Fe2 plus and Fe3 plus. And as it cycles back and forth between so it has a variable valence, a variable charge on it. It's a transitional metal. And as it cycles between Fe2 plus and Fe3 plus, it can give off electrons to oxygen and generate free radicals, generate superoxides. And these superoxides can also undergo, it can lead to a process that's going to lead to producing hydrogen peroxide and subsequently producing hydroxyl radicals. Okay, and these hydroxyl radicals can be very damaging to your cells. They can damage the DNA in your mitochondria, damage your inner mitochondrial membrane, damage other membranes like your plasma membranes of cells. They're real bad. So you don't want excessive free iron. The body can store a lot of it. It sequesters it with iron-binding proteins, but you don't want extra iron on board. Okay, and this is called it becomes an autocatalyst, and it can just generate a lot of these free radicals very quick and do a lot of damage. It's real common when you read about all the neurodegenerative diseases. It's very common that iron is involved in oxidizing brain cells. And there's other things get involved in that too. AL will get involved in that too, okay? And then it's thought that F minus that's put in municipal tap water stupidly can bind with Al, increases transport into the brain, and all of a sudden you've got all these oxidants. You've got the Fe, you've got the Al, and that is not good. And you've got a bunch of mitochondrial inhibitors too. You start generating this perfect soup, if you will, to just destroy brain cells. Okay, here's the inner mitochondrial membrane. And inner mitochondrial membrane has 5 complexes, and it's basically a bucket brigade of firemen. Instead of passing water along, they're passing they're passing electrons. They pass electrons from the weak grabber to the strong grabber. The strongest grabber of electrons in the mitochondria is oxygen. And as they pass the electrons down, they pump out a proton into the intramembranous space between the inner and the outer mitochondrial membrane. And now you've generated a gradient of protons. It's a really powerful gradient, like negative 160 millivolts. And that gradient can be harvested by allowing a hydrogen to come back into the mitochondria, to re-enter the mitochondrial matrix. And the energy from that spins this enzyme. Complex 5 is an enzyme, ATP synthase. And that energy produced from the re-entry of the hydrogen enables a phosphate to be coupled to ADP to make ATP, adenosine triphosphate, the energy of the cell. Okay, if you got free radicals being produced, because you always leak a couple electrons, that'll produce superoxides, and if you produce too many of them, it can overwhelm the neutralization system of superoxide dismutase, catalase, glutathione peroxidase. Anyways, the point is, you start making this hydrogen peroxide, and you got free iron around, it'll just grab it, make it into hydroxyl radicals, and those can trash the mitochondrial membrane. So the bottom line is you don't want high levels of iron. As a matter of fact, I donated blood, and I routinely pull off a couple tubes of blood whenever I go to get blood labs checked. And the reason I do it is I want to keep my iron low. I want to try to get my serum ferritin, which is a good indicator of body iron stores, between about 30 to 80. So that's worth remembering. Ideal serum ferritin is about 30 to 80. When I first started out, I was like around 270, something like that. Couple of years ago, because I used to eat all that Raisin Bran, so I had relatively high iron stores, and it takes a long time for the body to expel it on its own. So by just donating blood, or pulling off a couple extra tubes every time I donate blood, I got it down to somewhere like around 110. So that's going in a good direction. Okay, let's see. Why is iron overload dangerous? I kind of went through ferrous redox cycling. I talked about you can overwhelm your neutralization system for the free radicals made in the mitochondria. Here's about how iron comes in. Iron comes into the body, absorbed through the duodenum, and then it sits in the duodenal cells, and then it's picked up by transferrin to transfer iron around the body. And the transferrin molecule holds 2 irons. It looks like a little rowboat, or some people say it looks like a wheelbarrow, and it just shuttles the iron around the blood and takes it where it's needed. It takes it to the bone marrow to make red blood cells for the hemoglobin. Okay, it takes it to the liver. Liver stores a lot of iron and ferritin molecules. They can store like about 4,500 iron molecules to keep it tied up. And what do you need it stored for? Well, our ancestors had to worry about bleeding, being chased by a predator. And if they bled, they wanted to be able to replenish their hemoglobin rapidly. And they could do so by having iron storage available. For them, iron was more scarce in the environment than it is for us. Okay, if you have an acute infection, the body will want to sequester iron, so it sends a protein called hepcidin. It's a liver acute reactive phase protein, acute reactants proteins. And it will bind to ferroportin. FP is ferroportin, and it says, nope, do not let any more iron in the body. We're trying to minimize bodily iron because it'll help us to fight this infection by denying the bacteria availability of the iron. Okay, this NTBI is non-transferrin bound iron. You want to keep that to a minimum. And ferritin normally should only be intracellular, but some of it, when a cell dies, leaks into the blood, and that's bad. So the higher the serum ferritin, the worse, because the ferritin really don't belong there. The spleen is the graveyard for red blood cells. Typically, they die at about 120 days, then 3 months. We talked about that because they get more stiff, less deformable, less flexible because they're glycation, and because phosphatidylserine externalization, where the phosphatidylserines move from the inner leaflet of the plasma membrane to the outer leaflet, and that makes them less deformable. Okay, so that's how they're cleared. They can't go under the limbo stick, so to speak, getting through the tight capillaries in the spleen that are only about 3 microns in diameter, whereas the red RBC is about 7 microns in diameter. Okay, so we're going to leave it at there for today. Hope that was helpful.